Hello, everyone. Welcome back to the ARC seminar. Today we'll have Kiran and Shila, who will be telling us about types being good, actually.
So, all right, wait, where do I, oh, I'm looking here. Okay. Yeah, so we're going to talk about types, and this is going to be like completely different than the last talk in pretty much every possible way. Because to preface all of this, I read like a lot of Julia, right, in the last couple of years. And the thing I'm building now, the G-Rex telescope I'm working on, is like we have to build these servers out, which will do all the compute for each antenna. And I don't want things to break. Like I'm going to ship them to people all over the world and say, hey, please run this script now. And it would be nice to have confidence that it will actually run, and I won't have to be on the call with someone in Australia to like debug why the screen is full of errors. And so like as part of that, I had never programmed Rust before, and I started to, because it's like, well, this is like a systems language. This is a systems kind of problem. It kind of makes sense that I have an executable that will always work. And it has like changed my life. And I have learned that, types really are good, actually. And I would like to share this knowledge with you because I programmed in C and C++ before, and like I'm used to statically typed languages, but this is like really different. And yeah, we'll just get into the meat of it, I suppose. So talk about all sorts of stuff, but we're going to start with Python, which is kind of like in the same vein as talking about Julia, in the sense that if you just look at this function, you can ask yourself a bunch of questions, like what kind of data is valid for both X and Y? What does this return? What does this function do? When we run it, if you just saw the type signature, and when really what I mean by this, if you call it, if this isn't a library and you're accessing this function from somewhere else and you hover over it in your IDE and it gives you the little blurb about what it does, nothing about this signature really tells you anything. You would have had to rely on what the function was named, if someone named it properly, if they added documentation for the valid types of the inputs. All of this stuff was the burden of the programmer to like actually do, to give you like some confidence about how it behaves. So if new Python, we have typed annotations. They don't do anything in runtime in Python. And that solves like kind of the first part of this problem of what this function, the inputs and outputs, that kind of stuff, but that doesn't really answer what does the function do. And so, you can kind of think as in a lot of modern languages, you have a couple separate execution paths. What I'll call the primary execution path, where you have a function, it has some inputs and it has a type of output. I would call it, that's like the primary thing it should do. You give it some floats, it gives you a float, these kind of things. But there's all sorts of other things it can do. These are called side effects in the functional programming land, where it could throw exceptions, it could do input output, read from the command line, print to the screen, could spawn some async tasks that do something somewhere else. Those aren't part of the type signature in, say, a Python function. You have no idea if that function is going to do any of that until you actually run it, right? So this is a problem because the burden is on you, right? As an author of functions, primarily, you are in control of, really in Python land, the documentation of telling everyone who's going to use your function how it will behave. And so you have to make sure you get that right, which means you have to have a lot of knowledge about everything you're doing in the function, which is a pretty high cognitive burden, I'd say, especially with exceptions, which we'll talk about in a second. But you get to control when problems happen and how to deal with them, primarily, like if we simplify things. So this is kind of what people call the billion-dollar mistake. Specifically, the guy who invented null calls the concept of null a billion-dollar mistake, because it's we'll talk first about exceptions and we'll get to null in a second. But if you just think about exceptions, in a Python function, you can throw an error, which means there's now this separate path that happens that's completely divorced from your primary execution path. The thing which is like processing floating point numbers, if you're doing some crazy nonsense, in the middle of that somewhere, it can throw an exception. Like we can all agree that go-tos are bad, right? Like you've heard this mantra before that go-tos are bad. What are exceptions? Exceptions a go-to, except we've like agreed that it's an acceptable thing. And, you know, throwing an exception now forces you to think about this like branching execution pattern. And so instead of as a library author, the consumer now has to think about all these problems. And because it's not encoded in the type signature, you just have to have documented all the exceptions that can happen, and then it gets really complicated. And because you expect the user to handle any errors that you could potentially throw, why are these called exceptions? Why is this exceptional behavior? If the fact that it can happen and that someone has to deal with it, it should be called expected behavior. You know what I mean? Like this is a big problem. So, and like I was saying, it's not just null. If you have in C, you have a thing which returns a pointer to something, say, and if the thing didn't actually exist, it's like standard to return null. And now you just have to check against null. But this is a problem because the pointer type of null and the pointer type of a pointer to valid data is exactly the same thing. So if you just forget to handle it, you have runtime errors. This is the same thing as exceptions. If you forget to handle it, it's a runtime error. And the whole name of the game here, and what I was talking about with like this telescope system is, I do not want runtime errors. Once I compile the program, it should just work, which isn't really possible in Python. It's not possible really in Julia. It's not possible in certain subclasses of C++. You can be really fancy with C++ and do all of the things that I'm about to show you, but it's harder. So types to the rescue. There's a solution. We can fix this. And to begin our discussion on the solution, we are going to learn about algebraic data types. Algebraic data types is a term that kind of comes from the functional programming land, really the Haskell community. And this is I'm starting with the one you're actually not familiar with. And this is called the sum type. You might recognize the keyword enum that exists in a lot of languages, but it's different in Rust. Most of the examples I'm going to be showing here are in Rust, but the same kind of concepts apply to functionally languages like Haskell, OCaml, this kind of stuff. So this is what we call the option type. This is the generic syntax in Rust, just like C++, where you have your angles, and there exists some type T. And there are two cases for option. You either have some T or you have nothing. These keywords are now just values that exist that are of type option. So nothing is an option, sum of T is an option. And unlike enums in C and C++, your enums can contain data. That's why it's kind of a sum type. It's either some nothing, which doesn't implicitly just doesn't contain any data, or some which contains some data T. It's really pretty simple. And the cool thing about this, the implementation of this in Rust is this is usually a zero cost abstraction. So for types which I forgot, there's a fancy word for it, but they can do like null pointer optimization in the background to make this zero cost. It's not always true, of course, but usually zero cost. If it's not zero cost, it's like an extra word to store like which thing it is out of the two. If you were to do this in C or C++, this is called a tagged union. That's the equivalent. It's not an enum, but it's called enum in Rust. So if we look at how to use this in like these two different cases, if you see an error in my C, please let me know, it's been a while. But if I did it right, you can have some function called get, which takes an array, which is an int pointer, because in C you give it the pointer to the first thing, some index, and it returns to you. I know this isn't actually true for get in C, but say for the sake of argument, you return a pointer to the element in the thing. This is what the equivalent statement looks like in Rust. And here, if you indexed out of bounds, for example, you would check that in your implementation of get and return a null pointer. But the problem is an int pointer to null is the same type as an int pointer to an int. They're just addresses. There's no difference. In the Rust example here, we return a completely new type called option, whose value in that sum branch, this is the specification of that template type T, is a pointer to an int32. How is this different? This is different because this is a different type. It's an option. It's not an int pointer. It is something unique from an int pointer. And checking for null isn't always nice. This is JavaScript, in case you can't tell. I mean, who came up with this? I mean, the answer is Brendan Eich, and he wrote JavaScript in a week. And it's stayed this behavior for the decades since the week that he wrote it. Like, this is asinine. This is crazy. And so if you're writing a function that returns some like optional behavior, do you return null or undefined or nan if it's a number? Like, well, nan if it's not a number, but then like all the cases where you have to like compare it to something to see if you got a real data back or not gets hairy, because you have all of these different cases of like how exactly you're supposed to check for it, which is more you're pushing the burden on the consumer of your library to like know all of these details, which isn't, it's hard. For the case of exceptions, there's a wonderful type, which if you notice looks a lot like the option type, called result, except there are two different template arguments. You have T and E, which is a type in the OK branch and the type in the error branch. It's just like option, except now we have data contained on both parts of it. They're called something else called OK and error, but other than that, it's the same concept. You have these two different things that a result can be, and it's a different type. It's a different type than if I return a integer, I return a result. There's no exceptions in Rust. That's what this turns into, is you cannot throw an exception in Rust. You return a result. This means that the person who's consuming your code is forced to deal with the cases that it's exceptional. Unlike in Python, where you can just forget to put it in a try. Like, you write your code, you get some exception, and you're like, oh, shit, I have to put it in a try. And then you catch the thing, and then it throws a different kind of error. Oh, I have to catch this other thing. Like, you don't know until you run it. And that's obviously not a sustainable solution for big pieces of code. So in practice, what does this look like? So say I have an enum. This is more like a normal C enum, where I just have some names for different cases. And I have some function called do some math, which takes some integers, and it returns a result of an I32 or a math error. Now it's very, very obvious what this function does just by the type signature. You know that it's going to do some math with X and Y, and you're going to get an I32, but it could potentially have an error in it. In fact, you know exactly what kind of errors it could do. It could be a divide by zero, overflow, negative square root, these kind of things. It's all now encoded in the types, which means you can check it at compile time, which is really good. And this is backwards from the C, Java, every other language kind of model, where you now specify when your code will panic. When will your code crash? Because you have to handle this result somewhere. And there's a function in Rust called unwrap that if it is an error, panic. If not, return, grab the value contained by the OK branch of the enum. which is like the lazy thing to do, right? Then you have the same behavior as Python or anything else. But it's like it's an escape hatch. So why don't people do this? Well, it's annoying, right? Now instead of your function returning integers, it returns results, and you have to deal with it. But that's the benefit. You have to deal with it. You trade off your a little bit of programming time for the benefit of ensuring that your code won't panic. Which, I mean, that's up to you to decide whether or not that's a worthy trade-off. But to be fair, I'm not convinced that this is the best thing all of the time. It makes iteration time slow because you have a lot of code to write, a lot of boilerplate to like do the things that you want. But in certain kinds of systems, I mean, this is kind of worth it. I think it's worth it. And like for my telescope project, it's definitely worth it. Let's look at this from another kind of perspective. So very similar to what Rhiannon was working on. If we have this call here in Python, there are implicit assumptions baked into this expression, right? First, item's a hash map, a dictionary, and view count of item is also a dictionary. And both of those dictionaries contain the keywords view count and n, which are, you know, when does this panic? When will you handle when this panics, and how do you recover from it? That's hard. It's hard in Python. Rhiannon can attest to it, the fact that this is hard. If you wrote this same, and the last thing is whatever the thing in n is in this hash map is also, you can convert it to an integer. So this is what this looks like in Rust. There's this magical operator called question mark, which things that return results, you can question mark them and they will automatically return the error branch, so that you can imagine that this is inside of a function that also returns a result. This will just automatically return the result, or it gets the value, which becomes the the whatever the value is there, string. Same thing for n. Frumster radix also returns a result because it could potentially have invalid characters in it. Say if you're going to a hex, it could have non-hex characters. But this is what they call railway-oriented programming. Came from C#, I think, or maybe it was F#, where you have this primary execution path, just like what we were talking before, and you have all of these, and then you have a parallel railroad that is your error path. And at any point in your execution, you can bail to the error path. So you know how everything is handled, and you're pushing things up to where they should be, and all these things. And from a library author perspective, this is what you want to do. You know, you're describing where all the errors happen, not how to really deal with them, because that's on the consumer to figure out how to deal with them. If I'm writing an application, I'm just going to use unwrap and panic in the places where I know it's okay to do so. So, you know, if you look at these errors, null pointer exception, none type has no attribute, you know, this is a design decision in the languages that we use that these can happen, is what I'm saying. Like Python made the decision to have like the same kind of types. Like none can just exist all of a sudden and break all the downstream code, and you get this error, none type has no attribute, and you're like, okay, what was none? When did this happen? You have to dig through the stack trace to figure it out. Like, that sucks. It sucks, and it's not a programming language design problem. We can solve this problem, and Rust solves it. And it kind of comes from what Rust calls safety. But when they say safety, they really mean memory safety. But this has like a lot of implication. Like, I don't care about memory safety. I really kind of don't. But this has a lot of implications. So we're going to go down the memory. We're going to learn about the memory model for a second, just to get familiar. And Rust has what's called a borrow checker, which it uses. It's like the third way to deal with memory management. it was kind of novel when they came up with the concept. And that's why Rust is different from the other language. It's not just another language. So, you know, there's usually this mantra that there's two real ways you can deal with allocating memory. This is all about like memory at runtime kind of things. The garbage checker is popular. Java does it, Python, Ruby, Julia, Node, Go, all these languages, Haskell. They have a separate program that runs alongside your program that looks to see when data is no longer being referred to and then gets rid of it. This doesn't really have a runtime impact. Like I showed you in the examples from the last talk, Julia can be as fast as C, and C, of course, doesn't have a garbage collector. It just has latency issues. You have what are called stop the world GC pauses, where the other program has to say, hey, primary program, I need you to just stop for a second so I can see what's valid, so I can delete all the things, then resume execution. I would say that the most impressive garbage collector on the planet is Java's in the JVM. I mean, it's been had decades of improvements made, and it's really, really efficient at what it does. But I mean, you still have all these issues with the garbage collector. So Rust wants to solve, and also you have to have this whole runtime. Same thing with Julia and Go and all these things. You have this huge runtime you have to ship, which contains that garbage collector code. So how does this borrow checker work? It's kind of a weird concept. And I would say it boils down to two different things. You are tracking what are called moves, and you have lifetimes of a type encoded as part of the type signature of the thing. We'll look at the first one first. So if any of this syntax starts to get a little too hairy for you, please let me know so I can explain it. I've been staring at this for like months now, so I'm used to it. I know it's could be a little alien, but we'll have a function that does nothing called hold my vet, templated on some type T, where we accept something where I'm not binding the name because I don't care. And it has the thing I'm passing to this function has type a vec of T. And then in my main, I make a new vector which has some numbers in it. I call hold my vec on V, and then say I try to get the third element from V, which returns an option, by the way. This does not compile. And if we look at the error, this is the error Rust gives us, which hopefully is a breath of fresh air compared to C++ errors, where it's saying that the move of V occurs because V has a type of vector, which is not implement copy. It's moved here at the call to hold my vec, but the value is borrowed after the move when we call v.get. So get takes a pointer to the vector v and then tries to get a value out of it. But the problem is we moved the value of v into this function. And after this function is done with it, it didn't give it back, which means v no longer exists. This is weird. This is different than other languages you've probably seen before. You know, because nothing about this kind of obviously tells you that this won't fail. You kind of just have to get the hang of it. But it's, well, we'll see the implications of this. But it's saying that hold my vec is consuming the value v, which means it no longer exists in this main scope. So by the time you call v.get, v no longer exists. That's what this is saying. So this is the Rust compiler checking moves. The solution to this is you pass in a reference to a vector of t's. And this is fine. This works no problem. Because what you're saying is in the Rust terminology, hold my vec borrows this value, and it will implicitly give it back by the time the function is over, which is normal kind of pass by reference behavior. So sometimes the Rust compiler output will tell you like, consider borrowing. This might work. And for learning Rust, you can pretty much just do what the compiler tells you to do, and it will usually do what you want. It's pretty awesome. So this is going to get a little bit more tricky. Let's make a struct. And this struct contains, this is where the syntax gets a little wonky, a reference to a vector of type t, which is some any t. And then there's this thing called a lifetime. This is how you annotate lifetimes in Rust, tick A. And this is saying there is a tick aid borrow of a vec t is what ref is. Oops. The most confusing part about this, at least to people who are new to Rust, is that this is descriptive, not prescriptive. And what I mean by that is, at some point in future Rust, this is probably going to go, this syntax is going to go away. The compiler could figure this out without saying that, okay, the lifetime of this struct, the places in which instances of this struct are valid is the same as the places which the reference to this vec A is valid. That's what this is saying. They share the same lifetime. And to put it more bluntly, when I'm going to make some vector somewhere, I'm going to get a pointer to it. By the time the original vector doesn't exist anymore, the danger boy also must not exist, because then you'll have a dangling pointer. And by tracking that the lifetime of danger boy is the same as the lifetime of this vector, means that at compile time, you guarantee that doesn't happen, because it's part of the type. If you use this in a context where this lifetime is not valid, that's checked at compile time, which is super cool.
Wait, so can I ask a
Yeah,
question?
yeah.
So if you have multiple attributes, right?
Yeah.
Then and you're saying that in a future version of Rust that somehow the compiler would figure this out, but then how would that be the case?
With multiple things?
Right.
Yeah, so it does lifetimes are contravariant in Rust. Well, it will take the union of all the lifetimes. Intersection.
So what does that mean? Like,
So if you, yeah, the minimum lifetime.
Okay.
This isn't really it.
okay.
It's not a time. It's like they say lifetime, but they really mean scope. So it's
So just if I lose any of them.
The first one to go out of scope will invalidate.
yeah, exactly. And which gets kind of tricky and potentially really frustrating, because you're like, oh, I need this to live longer than it does because I'm using it, but Rust is forcing you to think about these things. Is kind of like the implication of that, right? So put this into context a little bit. We have this same kind of function from before, work with vec. Now we have a work with danger boy. Kind of the same thing. Template with t takes a danger boy by value. I might add. Does nothing with it. Do the same thing. Make a vector. We're going to make a danger boy. This is how you initialize a struct in Rust, where we say ref A is given a borrow to x. They're called borrows, but it's a pointer. Except it's a pointer that's being tracked with all of this lifetime stuff. And then we call work with vec. This actually works fine. This compiles no problem. And which might be confusing at first because, well, you know, we're moving the value of x into this function, which destroys it. But the compiler is being smart and saying, well, DB is not being used by anything after this line, so we really kind of don't care. And in fact, you'll get a warning saying, hey, this is an unused value. But if we do more things with it, say we call work with danger boy, which takes the danger boy by reference, it'll say, no, you can't do that. You can't do that because work with vec, moved X, it consumed its value, and now you want to consume something which has a reference inside of it to the thing, but now the lifetime is gone, the lifetime is no longer valid. So it can check this at compile time. They call this like wrestling with the borrow checker, because it's going to give you errors in a lot of places that you're not used to having errors. But again, this is good. This is eliminating entire classes of problems in a lot of static type languages. So you don't ever have this with garbage collected languages, because you have this other program that's at runtime checking when data is valid or not. It's not a compile time thing. But then it's not a compile time thing. In some cases, you want this to be a compile time thing. But having a type system that can introspect what your code is doing at a really, really low level as part of the type system, this solves like a whole bunch more stuff than just memory safety. For example, if you look at the sticker on my laptop, invalid state should be unrepresentable. This should be your mantra from all programming from here on outward. You should internalize and say this 5 times a day, that invalid state should be unrepresentable. For example, we have some enums. Living is either alive or dead. You have some Earth continents with the 4-continent model of the Earth. You have some planets, and say we have some human, has a string of a name, has a state, whether or not they're living or not, has some planet. And if the planet is Earth, it'll have some data contained in it that gives you the Earth continent. Every time you build a thing of type human, it will have valid information. If these were all just strings, it could be gobbledygook that isn't necessarily what you want. This is a pretty simple example, but the idea is the type system is smart enough such that if you're very careful about defining the layout of your data and stuff, you can make it such that you cannot build instances of your data that are bad, that are bogus. And if you do this, this is a contract that the compiler will hold you to and hold anyone who uses your code to. And that's what you should think of the definition of your data as a contract, right? And if you put into your contract that things can just have gobbledygook in it, well, then you should expect that to happen, because it's the real world and people make mistakes. And so and Rust, this is no runtime cost, right? Just specifying all the enums, and it's really tight or space efficient too, because the compiler is really good. You can do this in Python. Just the other day, I was interacting with some code where it's comparing against a string, but there's only 5 different things that string could be. And of course, they use a string as the input because that's what makes logical sense. You're comparing against a string, but I could pass anything into that function, and then you have this runtime error. And you would have had to insert another case in the if it's none of these things I'm checking against, then panic. Which means you pushed the burden of that being correct to the user to deal with the fact that it's going to throw this exception. The alternative is enum is a thing in Python, not some types, but like boring enums, like alive or dead, this kind of thing. You pass an enum to this function. It's a little bit more programming work because you have to assign values of each enum to the string. You can do this in Python where you say the enum variant equals the string it represents. And then you use that to compare. So in your function, you accept one of those enum variants. Now you know at compile time, when the code starts running, that arguments to that function are going to be correct. And this is a much better way to code, because you get these, you solve these problems up front instead of it happening at some unspecified time later. So if you're wondering what kind of state, like realistically, what kind of state can you force to be unrepresentable? A lot. in Rust. The type system is good enough where like legitimately the entire Windows API, all of WebAssembly, for certain microcontrollers, just as a little blurb, in microcontrollers, certain pins can have different kinds of behavior. It could be an output, it could be a digital to analog converter, these kinds of things, but it can only be one of those at a time. In the C implementation, in the assembly implementation of the microcontroller library, it's just like a flag. You have some bit set, and it's one of those things in the bit. Well, you could just set them all to 1. And then what happens? Who knows? Does it catch on fire? But you could encapsulate that in Rust in, say, an enum. And when you build the instance of the pin on the microcontroller, it is only ever one of those things, which means at compile time, you will never represent invalid state. Because invalid state should be unrepresentable. Because if it's unrepresentable, you eliminate all sorts of problems. And spoiler alert, in the Linux 6.1, which is going to come out soon, there's going to be Rust in the kernel, which Linus does not like. They thought about C++ in the kernel in the late 90s and immediately trashed the idea because it's too much. There's a whole Wikipedia page just devoted to complaints against C++. It's the only other language besides C89 and assembly that will be in the kernel. And if it's good enough for Linus, I mean, you know, it's not just me, you know, talking about it. This is also going to get a little bit more on the technical side, but here is a C function. What should this function return? Give you a second. You take 2 pointers, two pointers to an int, assign the first one to 42, second one to 99, and you return the value of the first one. What should it return? Anyone? Assign the first one to 42, then something else happens, and then you return the value of the first one.
I've never programmed in C, but I would assume 42.
You'd assume 42. If you were an optimizing compiler, would you think to just have this function return 42? I mean, other than the side effects of the assignment, you would think to just return 42, because obviously that's all this can do, right? Uh-oh. So if we look at the assembly for a second, and I'm sorry for the people who aren't so familiar with assembly, but this is not what the optimization all the way up on GCC does. This is doing exactly what the code said, where we are assigning value pointed to this, 42 pointed to that as 99, and you return, which is the result register, whatever is in this memory location. It's exactly what it says it will do. It did not just return 42. If you look at the Rust version, which is the same thing, you have a mutable reference because that is a different type than normal references. To an integer, mutable reference to B, you return an integer, same thing. And the syntax is really similar to. It's functional style where there's no, you can use return, but the value of the last thing is the value of the function. You will notice, instead of putting into the result register the value of the RDI, it's inlined the value of 42. Because Rust is making an assumption that C could not make. Specifically, Rust, one of the rules of the biochecker is that you are only allowed to have one outstanding mutable borrow for a given thing. So if I were to call this function, you have assign these to zeros, you have to declare that values will be mutated in order to take mutable references to them. And you would call the function with it. This does what you'd expect. Well, what if we want to do this? And this is the case you might not have immediately thought about when looking at the C. This is a contrived example, but it's simple enough where we can look at it. If we want to pass in the same thing to both places, well, then obviously 42 is the wrong answer, right? Because both of those pointers will point to the exact same place in memory, and it should return 99, because that was the second assignment we did. This is called pointer aliasing in general, and if you want to read the couple thousand page C standard, it talks about the behavior of pointer aliasing in functions and when you have undefined behavior due to pointer aliasing. Rust will not compile this. Rust will say you have a mutable borrow here and then a mutable borrow there. You can't have two mutable borrows for the same thing at the same time. Problem solved. The optimization Rust made to return 42 is because of its memory model. Because you cannot have pointer aliasing just ever, then it can make these kind of optimizations. In case you didn't know, you can actually do this in C as well. There's a keyword called restrict that no one has ever heard of that allows the C compiler to do the same thing. You would have had to read the couple thousand page standard manual and know about the behavior of pointer aliasing and learn about the special keyword restrict. Just to briefly say, there is a thing you might think that this is limiting for Rust to have these kind of strict rules. And there are certainly cases where you want to do something efficient with some really hacky bit manipulation bullshit that, to squeeze that last little bit of performance out of something. Rust gives you this thing called unsafe, which allows you to do things that the borrow checker would not normally let you do, which is useful for a lot of low-level stuff. And the benefit is it's only in little cases where you have to annotate it with unsafe, and it's easier to audit, I would say, because you can look for all the places that are unsafe and apply extra scrutiny to those things. In this case, we are casting the mutable borrow of n to what Rust calls a raw pointer. It's the same, it's still just an address, but the type system treats them as different things. And we can take a mutable reference to the value of that raw pointer, this is a kind of roundabout thing we have to do. But this lets us now have two pointers to the same piece of memory and call this function. But this is going to return 42, which is wrong. It should return 99. But we didn't change the definition of the function at all. We just called it incorrectly, right? This is the assembly of that function. It returns 42, full stop. And just because we sprinkled some unsafe stuff around it doesn't change fundamentally Rust's memory model. And this is kind of an important distinction. Some people say, oh, unsafe Rust is basically C. If you want to turn off the type system for these kinds of things, you just can, and it will behave like C. This is not true. The type system and memory model associated with that type system in Rust is part of how the compiler works. And there are certain invariants that you just have to satisfy. And this is much like the example with the C code, where you would have had to know. This is a backwards example for Rust. I'm showing a case where Rust is kind of weak in this regard, where you would have had to have some pretty deep understanding of how the Rust compiler works in order to catch this mistake. But I mean, we can find the source of the error easily because there's a big unsafe block which is screaming, hey, you should pay extra special attention to me because I might be doing something bad. And in fact, if you have you ever used valgrind in C or C++? It's a really phenomenal project that will check for undefined behavior in C and C++ programs. It's a really, really incredible static analysis tool. There's one called Miri in Rust, which would have instantly said, hey, you're violating one of the invariants of the compiler when you do this. So if you're writing any production, super critical, mission critical stuff in Rust, you'd want to run it through some tool like this to make sure that you didn't accidentally violate one of the compiler invariants. Yeah, and this is stuff I just said. So kind of to wrap up more or less, Rust is not a faster horse, right? Borrowing from the he who must not be named, who makes cars, made cars. But the point I'm trying to get across is that encoding correctness in the types is kind of an unfamiliar way to solve problems. We're not used to coding like this. It's not a better C. Some people say, oh, Rust is a better C. It's not a better C. And we've shown this. Unsafe Rust, which people say is basically C. It's not C. It's like you have this whole other complexity of how memory model and type system works, which you just have to know. If you want a better C, try Zig. It's quite a good language, actually. It's not a better C++. You don't have classes because it was a mistake. Try Go if you want a better C++ or Carbon, both Google things which will be bound forever with your lifeblood to Google Corporation if you want to use them. But do you want a better C++? Like if you're reaching for another language, do you want a better C? Do you want a better C++? Is that really what you want? No, because people would want a faster horse. Like, oh, I have my horse. People don't people would say they want a faster horse, right? That's what they're saying. Is it better than Python? Is it better than Julia? It's better than Ruby? Well, there's no runtime types. It's not a live codable language. In these languages with runtime types, the burden is on you to kind of envision the concrete types of everything, and you have to keep that mental model in your head to make sure things are right. Well, in Rust, you switch that burden to the compiler to check. That's not on you anymore. So it's not really better than any of these languages, it's just different. But the benefit of this is it's something completely different. You can take these patterns away to the language that you use, but the idea is with a strong enough type system and being really, really careful about making sure, as to the best of your ability, invalid state is unrepresentable. You solve so many problems. In concurrency, you eliminate race conditions like this. You don't have to think about seg faults because you will always have valid memory. Your code will probably work the first try. I've never had this happen as often as it does in Rust, where my code works on the first try. And that's because it never builds on the first try. You sit there going back and forth with the compiler for an hour while the compiler finds all the places in your code that you made mistakes. And that means that your compile times will be long. But the result of all that is your code can be perfect. You can write perfect, correct code, provably correct code. And that's powerful. That's powerful in math, it's powerful in control systems, it's powerful in all sorts of places. They do this for proofs. You can write proof assistant languages if you have a strong enough type system. Your code can be perfect. Give it a shot. All right, that's it.
Any questions for Kiran?
Yes.
So what if you want to parallelize your Rust code? Is that possible?
Mhm.
Is it difficult? Well, any more difficult than it would be in another language?
So there are a couple of weird things in the Rust concurrency land, concurrency and parallelism land. You can spawn threads, no problem. And part of the memory model is it will track to make sure threads have their own the things they point to are valid. In fact, have you ever used mutexes? One of the common ways, if you have two threads which are trying to interact with the same piece of memory, a mutex is just a thing which says it's a thing you can check within your thread to say, oh, is someone else using this right now? I'm just going to wait until it's clear and then I can use it, which eliminates two things trying to simultaneously muck with that data. In Rust, it's an enum. It wraps the data it contains. In C and C++, they have like this extra field. So they have a lot of these really nice concurrency primitives like mutexes. But it's no harder in the sense that you have to obey all of these rules, and these rules are extended to multi-threaded stuff. There's an attribute called send and sync. If you can send it to another thread, there's only certain types which are able to be sent, which is tracked in the type system. But there's no async runtime in standard Rust. You can call threads no problem, but if you want like the concurrency stuff, like async in Python, Go threads in Go, green threads as generically in other languages, there you have to use like another library to get async, which is a little frustrating. I know people don't like that. It's like obnoxious to have to pull in a library if you want to do async. Threads are easy, but also threads are heavy because it's another thread. It's running on another core, probably. The operating system has to decide where it actually goes. But yeah, it solves a lot of concurrency problems, I'd say. Which means that yes, it's harder. Because it has to be, right? If it was easy, then it's fewer things that you could check. Yeah.
So back to the exception stuff. Do all functions in Rust return results, or is it
No, only the ones that can fail.
one of them? So what if you have like nested functions that can fail? The top one may not know what the inside ones are going to throw as errors, so how can you know that beforehand?
But it does, because it returns a result and the error has a certain type. And
Do you have to specify that then? So if
Uh-huh.
I have two functions inside of a bigger function,
they return different types of errors.
they get two different types, and then I like put it into the top one, and then I added just another function down here, and I could re-edit the
Uh-huh.
outside function. So if
Uh-huh.
I have like a nested 50 called
Uh-huh.
I have to know.
Yeah, it's actually really annoying, and that's one of the things that's really kind of frustrating in Rust. And there are crates that help. There's one called this error. There's another one I can't remember the name of, which because you have all these functions, they have all of their own special kinds of errors, and your thing just has to be, okay, it could be any of those. And now you have to make your own enum that just contains all of them. And that's a lot of boilerplate that you just have to.
Can it not just analyze the functions that are called within it and then concat them all into one?
You'd think.
No?
There's some of these crates which is what Rust calls libraries, helps with this. There's like some macros which do it. There's also, you can use, if you've ever used runtime types in C++, like the whole RTTI system with V tables and all the bullshit, you can actually say that your error branch, I think there was a bullet somewhere which says you don't have runtime types. That's not true, really. You have runtime types in the same way that C++ does with the whole RTTI system. And instead of them being classes, because there's no classes in Rust, you have what are called traits, which are the interfaces of Rust. If a struct implements a trait, the trait defines the methods that you must have for the thing of that type. Error is a trait which has some methods. And so you could say in your error branch that will return something that implements error, which then becomes a runtime type thing. And there's a performance overhead, just like RTTI and C++ for this. And Rust really wants you to write the giant fucking enum that has all the all the cases in it.
That seems prohibitive in some cases.
And that's when those other crates, they're it's an active discussion in the language design people. Yes, this is annoying. How do we make it better? But yeah, that is absolutely one of the downsides.
How often do you want to use like unsafe and Rust? Like, are there good use cases for it?
Almost,
Kind of like a plug.
almost never.
Okay.
Yeah, you have to have a pretty damn good reason why. A lot of crates even there's a little compiler thing you can put at the top of your code which says forbid unsafe. That will guarantee at least all the code that you write, you're not using any unsafe code, because that's something that someone else has to audit. And actually, a common complaint against Rust is that it's a house of cards. Like, you have all of this perfectly safe code, but at the very bottom of it, you have this giant stack of unsafe code that has to actually interact with hardware, because you kind of need unsafe code to interact with hardware. If that unsafe code is bad, then none of it matters, is kind of this argument. This isn't really true, because you've distilled where the problems can happen to like a single place annotated with unsafe. Then you have a lot more people who can analyze that to make sure it actually does what it's supposed to do, instead of it just happening randomly in other places. I have only had to write unsafe maybe once or twice, and that was in places that I was in like a tight inner loop and I don't want it to do a check or something, because a lot of the times the safe code will just have some internal unsafe code and then just does the check to make sure that the thing it's going to do that's unsafe is actually safe, and then does the unsafe part. And if I'm in a tight inner loop and I can't afford to do that check, and I know, and I'm telling the compiler that I know this is fine, and then I can call the unsafe code directly, then that's like a place we use it. And the style in Rust is you actually in the place you use unsafe, you add a doc string called safety : and then you describe what you did to ensure that it's safe. And this will actually be exported in your docs when it creates the documentation, so people can read your excuse and determine whether or not they agree. But again, this is all for like auditing reasons, right? And yeah, so very, very often, or the opposite of that, very infrequently.
How come you have to use it when you like interface with hardware?
So in the case of a microcontroller, which is kind of a specific example, but when you're compiling to microcontroller code, they're going to say it uses what's called memory mapped IO, such that the interfaces to all of the input outputs of the microcontroller are exposed to you as just positions in memory. So for example, they could have an analog to digital converter, which, okay, so on this pin, you'll get a byte 0 to 255 of whatever the analog value on that pin is. They're going to say, once you enable that and set that pin configuration up, all that stuff, this position in memory will now just contain the ADC value. There's no way for the Rust compiler to know that. And if I just want to dereference the value at that memory location, that's an unsafe operation, because the compiler doesn't know that that's a valid data. It's a random memory location. So you have to use unsafe code for that.
Sure.
And this kind of pops up in like kernel level stuff. In pretty much, I would say like 99% of normal Rust libraries, you don't need to. Some people use it as an excuse to like go faster, to skip these kind of checks and stuff. But like even still, very, very few crates, even the really, really high performance ones, don't use unsafe code. It's not usually a performance penalty. Yeah.
No one else? All right, well, let's thank our speaker again. Next time is 1 week from now, and it's Kyle who hasn't told me what he's presenting yet. So
But it's gonna be ingredients of a video.
Okay.
is what you need to do to run a.
Fantastic. All right.
Yay.